We have one more speaker tonight. This is LaMar. She is an associate research scientist in the Center for Advanced Psychometrics at Educational Testing Service. Her current research focuses on the development of psychometric models appropriate for use with complex assessment tasks such as simulations or games. And today she's going to talk a little bit about how to use Markov decision processes to understand student thinking.
So, following on Bob's talk, I'm going to sort of continue to talk in the educational task domain. As Jim mentioned earlier, my work is somewhat related to the work he's doing now, but as I said, the time scale is different because we're talking about a task a student is doing over at most an hour, not a lifetime of decisions. So that does have a lot of different effects. What happened to the clicker there? I mentioned earlier that I have a background in science. And if you look at science assessment tasks, so this is a task that was in the California State Assessment, they would generally look like this. And this is what Bob was referring to with the standard educational measurement paradigm. And among science educators, this has been considered problematic because it really looks nothing like real science. Now, we would love to be able to send all of the students to the Large Hadron Collider and have them build a detector as an assessment, but obviously that's not practical either. So we're turning to technology and simulations as an ability to give students a way to express science, understanding their processes, the way they approach science that is closer to real science than the standard assessment items. Now, ideally, you could assess science skills by giving students some equipment and seeing what they do. They would have a lot of variance in their performance, and a lot of that variance would be explained by many different factors. What was their goal? Someone just brought that up. What is it they're trying to do? How much do they care? If they're working in a group, who's contributing? How much are they contributing? Do they understand even how the equipment works? Not to mention the things that we normally think we're trying to assess, like are they using good inquiry skills and do they understand the science content? So we can give these labels and talk about them as skills or attributes. They're all things that are important to the performance, to the variance in the performance that we see when students are given open-ended tasks. One of the advantages of the old style assessment and why it has been so very successful is that it eliminates almost all of this external variance. So by making the task very specific, very clear, not allowing people to talk to each other, and consequently also not allowing them to experiment, we can focus in on science knowledge and we can get a good reading on that. But it's not what the science educators really want, because they know that science is about a lot more than science knowledge. If we give them a simulated set of equipment and see what they do, all of these factors now are going to come into play. Well, maybe not collaboration, but there are some of these that we are working with collaboration. And my approach has been, let's model all of these factors. Let's see how they interact to produce the performance, and then hone in on the factors that we're actually interested in.
I have a question concerning both these tasks and also the task specificity that was presented earlier. So what's the outside option? So do you give people, do you let people do this and you tell them you're going to do this for half an hour and you're going to observe what you do? Or do you give them the option to do it, and if not, they can do something else? And if yes, what is this something else?
I mean, that's going to be very dependent upon the educational situation. There are simulations that have been put in some of the higher stakes tests. PISA, I believe, has some that they've done. In that case, it's just part of the assessment. Students are expected to do them. Okay. So Bob mentioned latent trait models. I'm not sure he used that term exactly. I just want to mention that my approach is based on a latent trait model, but in particular, action choice is being modeled. So the observable of interest is the actions that students choose while they're running through a simulation or a game. So I'm going to talk a little bit about a particular game, and then I'll give you the overview of the Markov decision measurement model and show you some examples of using it. Now, I don't know the economics literature all that well, so excuse me if I'm explaining things that are too simple or skipping over things that are not within your vocabulary. Let me know. Okay, so most people probably are familiar with the peg solitaire game. It's an old-fashioned game. The goal is to leave as few pegs on the board as possible. You jump over pegs to remove them. My question in this, I use this for simulation study, is can we take the action students take within the game to estimate their ability? If we use this as a traditional item and used only the outcome, did they win or lose, we'd probably have to have them play 10 to 20 games to get a good reading on their ability. So for a very simple board layout, this is, oh, that didn't actually work. Okay, well, there was an animation showing you how it works. Here's a simple board layout. You can win this game in 5 moves, and here are the 5 moves that you would actually use to win the game. The larger boards are much more complex, but what we're looking at is this is our data. So we want to know from the actions the students take, how good is their strategic thinking ability.
And is this timed?
No.
No.
Well, this is a simulation, let me say.
No.
But in general, it would not be timed.
Is that the only way?
Is that the only way? No, not at all. This particular game sequence can be also reflected in the game state. So in this case, the board reflects the state of the game at any time. So we started in this position. We jumped this peg up over here. You can see basically all the moves reflected until they get to one peg at the end. These 6 game states are just a subset of the full state space. So these are all the reachable states of this game from this starting configuration. So there are 22 states, and there are multiple ways to win, and there are also quite a few ways to lose. The basic idea here is that each individual state presents a choice. And these are the actions that are legal, given this game state. And the students are going to choose an action. No matter how they got to this particular game state, they now have to choose an action to move forward. And we want to model their action choice based on the latent variables that we're interested in. So what I propose is we use a cognitive process model, actually model the sort of planning and strategic thinking they might be using. And in particular, I'll be talking about the Markov decision process model for this. For those of you who are unfamiliar, the Markov decision process is a model for sequential planning in the presence of uncertainty. It was developed originally for robotics optimization in the 1950s. I don't know how familiar it is in economics, although you guys have all used terms related to it, so I suspect it's very familiar.
The whole society development equation.
Awesome. Recently, it's been used in cognitive science to model how we infer another person's beliefs and goals based on observing their actions. And this was really the inspiration for the way I've been using it here as a measurement model. So I'll skip over this because you guys all know it, right? So basically, there's a state space and action set. The transition functions are very important here. It's the probability that you'll transition into another state given an action taken in state S there. And then, of course, the reward structure, which gives you the cost or payout for taking a particular action in a particular state and arriving at another state. From these, we calculate that policy, the all-important part of the latent measurement model, which is the probability of taking an action given the state. So we want this probability to be a function of the value of the action. And so we use the expected total rewards, which is, since this is a sequential planning process, it's the summation of the immediate cost and the expected future rewards. So obviously the reward structure is going to impact both of these elements. The transition function, though, is also going to impact the expected future rewards. So I might, and it was referred to earlier, I might make an action not because I get an immediate reward, but because it's going to set me up to be more likely to get a future reward. And this is quantified in the Q function, where the value of choosing an action A in state S is the expectation of immediate and discounted future rewards over the transition probability. Yes?
This game is not stochastic, right?
The game that I showed you is not stochastic, but the framework, the model, handles stochastic transitions. And there will be some examples I'll show you later that do have that, a stochastic element. But you're right, these things get simplified if state transitions are deterministic considerably. In robotics, they solve for the optimal policy. The only thing they're concerned about is having the computer do the best action at any time. In psychology, they use the Boltzmann policy. And here, the important thing is that this beta parameter, which is considered a noise parameter, basically controls how optimal the action choice is. The higher beta is, the more likely the student is converging to the optimal policy. Closer beta gets to 0, the more students are just choosing an action at random from the available actions. Now, making this...
It's deterministic, right, in some sense. I mean, the Boltzmann is a version of the optimal, the more general policies.
Right, so yeah, exactly. If you set beta high enough, it becomes the optimal policy, right? But the interesting thing is, in the AI or robotics world, because they know they're solving for the optimal policy, that actually simplifies the calculation of the Q function considerably, because this probability of action can always be determined. All future actions are going to be the optimal action. When we use it in psychology or measurement, we can't make that assumption. Students are going to make mistakes, and they should be planning for making mistakes. That's part of the strategic element of this. So my first approach to using this as a measurement model is to focus in on this beta parameter. So I call it a capability, and it's really the cognitive part, so the cognitive model part, which is what is their strategic planning ability. And here's what the full measurement model would look like. But the important thing is that this is a cognitive model. So the whole Markov decision process is going on, we assume, inside the student's head as they're deciding what move to make next, which means that their goals are going to be the reward structure, and their beliefs are going to be what we see in the transition function. Another way of thinking about this is, while there may be an objective reality out there that gives them the extrinsic rewards and has the environmental state and system dynamics, their decision making is dependent upon their interpretation of those goals and rewards and their own understanding of the system. Now, educationally, this is really interesting because a lot of times we're trying to get at what their misunderstanding is. We want to know if they understand how a science experiment should go.
So the beliefs are going to be about the parameters of the Markov process, which is the persistence and the what else? What is the
So the beliefs are actually the transition function parameters. So the way this has been cast is that the transition function tells you, if I take an action, how is the world going to react? So if they have a different idea of how the world will react when they take an action, that's a different belief, and they get a different transition function.
Oh, so they form beliefs about the function itself, like the function.
They form beliefs about the world. We use the function to interpret them, or to estimate them.
So are they daisy and updating, or is there some, what's the model of changing beliefs?
We assume for this that they do not change beliefs over time. Now that, in a future work, I hope to get to that, and there's a whole...
It's like putting in a heterogeneity parameter in a Markov transition function. So we want mixtures on these.
Right. Well, at this point, I'm dealing with mixtures at the population level, but for individuals, we're assuming that they have a fixed belief about the world.
Individuals do,
and
but
fixed.
you aggregate over
Yes.
these different
Yes.
beliefs in this sense. Right?
Yes. So, so this is how the parameter space works. We're using beta as a sort of cognitive trait indicating decision making. The reward parameters tell us about both goals and motivation. They do a double function there. And the transition parameters tell us about the belief. Now, if we were to try to estimate all of these, we would definitely have an identifiability problem for most of the data sets I've seen. We just don't have a long enough trace over a complicated enough problem space to be able to pull all of that out. But we have choices about how we want to treat the parameters. If we feel that everybody understands the rewards that we've told them ahead of time, we can just fix them. And that's what we do in standard assessment. So it's really not as horrible as it sounds. On the other hand, we can estimate them at the population level. We can just assume that everyone has the same rewards. Or we can have mixture models. We have groups where we say, well, we know people have different levels of motivation, but we're going to assume they fall into 2 or 3 groups.
Would you vary them?
Or
like
be the person.
Confront individuals with different reward structures. And then how did that get identifiability?
We are not, I don't really mean by confront.
No, just give them, face them. Like, if you do the task, you get this bonus, you get extra
so
number of dollars than somebody else.
So the rewards I'm talking about are their own internal rewards. So we assume that we've told them ahead of time. So SimCity is a good example. They have the badges. So part of the SimCity setup is you can get different badges depending on what goals you achieve within the simulation. But that doesn't mean just because we're going to give someone a bronze medal for achieving goal X and a silver medal for achieving goal Y, that they value silver twice as much as bronze. The amount that they value it is an internal. The amount.
Why not just pay them? I mean, yeah.
Because this is an educational assessment. I would still say, though, if you pay them, people are going to still value it differently. The assumption that if it's money, it's all equal, I have trouble with that.
That's not what you need. You have monotonicity and payoffs. That's what you have. It's
You
not
can
a
give them
test.
different scenarios. You're a good person, so you can make them internalize without giving them money. Right? You're a really good person if you can achieve this goal.
I love this.
Quick question. I think in the paper you referred to T as the knowledge that you're trying to assess. So the data is the knowledge. T is a set of.
T is the beliefs, but that can be knowledge depending on how you set up the assessment. So if you're particularly talking about the paper that has the microbes in it, right, which I think is the one I uploaded, and I'll show that a little bit later, but the beliefs about how the system worked was the knowledge. We assumed that their knowledge.
The knowledge you're trying to assess.
Right.
And then the other thing is that aren't they, I mean, in terms of rewards and so forth, aren't they sort of getting, by winning the game, they're getting closer to winning the game, they sort of know whether they're winning or not? They're getting feedback on whether they're getting close, like in the one where they're going back to Earth, they're learning are they getting closer to Earth or not, or they're getting zapped by a meteor.
I played this game myself. I could never tell if I was actually getting to the end, right? I mean,
The peg solitaire game? It's
it's
challenging.
So the T is the transition function.
The T is the transition function, and
Do they know? In SimCity, they don't know T, right? They have to find it out.
Yes.
So but are you thinking in terms of model-based and non-model-based theories of that? I mean, there is a huge literature now in neuroscience that tries to pin
Yeah,
that down.
in SimCity, we're not even trying to model it. We think something like that is happening, but we're not modeling at that brain size.
Okay, but isn't this a crucial aspect of the entire exercise?
Uh,
How you deal with the uncertainty about the T?
In SimCity, we're not looking at that brain
Because
size.
it's too complicated. You can make a simple
Yeah,
map, but it's easier.
but in
to-
another sense, that's not part of what the goal of the SimCity is. The SimCity goal is for them to play the game enough times so that they finally realize that they better put up new power plants before they bulldoze the old one. So whatever their T is, I mean, maybe, there are some people who figure that out the first time. There are some people who play it 10 times to get there. Their beliefs are changing as they go along much more than the other person. We're not trying to model that. We're just trying to get them to the end. It's a very different goal that we have.
So-
I understand. Quick comment.
Well, but you said you might think about learning, right?
Oh yeah, it's all
So that would
possible.
be something you could build in.
Yeah,
Listen.
and we haven't.
Yeah.
Our goal in that game is to get kids, however they change, however many times, whatever their motivations were, to finally get to a state where they believe that bulldozing an old one before they put up a new one leads to bad things.
But then you're putting in, you're putting in an environment of doing the same repeated task over and over again. But then there's the larger question, I want them to, like we were talking at once, they sort of adapt to a new situation. So then the adaptability would be the kind of key for him, right? Learning.
Well, even within the SimCity game, I should say there were multiple missions. So
Yeah, you can play the same mission a number of
Bob and I are
times, but
both
each,
talking about one mission, but there were
Yeah.
other missions that they
yeah,
would
each
then
one is more
go into
challenging, so there are more
accomplish.
things you have to figure out about a new system.
So there are multiple levels. You had a comment?
Yeah, quick comment. If you pay subjects, it doesn't have to be money. Wait. The assumption is not that people would, universally perceive this reward as equal.
Mhm.
What you need is an ordering, that they would prefer better outcomes over worse outcomes. And that's a very weak assumption as long as they are not saturated in this reward medium. For example, money, but it doesn't have to be money. So I think if that is a crucial assumption that you want to make, that the goal system or the motivation is fixed, I don't see why you should not or wouldn't want to use some kind of reward medium. That's the comment. The
Okay.
question is, do you believe that this is an appropriate conceptualization of how people play this game? I don't. And are we talking about one game or a sequence of games? What if they just try out, experiment, see for solutions? Do they really anticipate, future moves, etc.? Are beliefs fixed? I haven't understood what beliefs really mean here, but conditional on the game having been evolved to some extent, beliefs ought to change, right? I learned that my strategy, if I had any at the beginning, was not the right one, so I have to adapt in the meantime, and I don't see how anything could be fixed here in terms of if I understand if my conceptual belief is right. I mean, maybe.
Right. So the focus of this early work was to take fairly small, enclosed situations
Why do you need
and get an estimate. Sorry, go ahead.
I mean, why do you need a model like this in the first place? I mean, why not just look at how people play the game and how successful they are, if they get better, how long it takes, how they solve the game, what type of strategies they use, etc., etc. I mean, it's all deterministic, as been pointed out, right? You can easily count steps, conditional on each move, what is the right or the optimal move, conditional on how the game has worked, etc. Why not just, in some sense, count it? On top, I mean, complexity goes down dramatically, as the game evolves. The last step is
What exactly are you counting? I'm curious.
well, you have to, you could classify. I mean, the first move is probably the most difficult, right? The most complex one. If it's
Departure from
the fewer pieces are on the board, the easier it gets, right? If it's only 2 pieces left, I mean, it's very simple.
Yeah, but it's the whole general strategy of when you're in a new arena, you start out with very simple problems.
All I'm saying is, you see what people are doing. I don't see any value added in transforming gameplay.
Well, the
value
value added is our knowledge about how to use models like this for games and for simulations that are not as simple as this one. We have to figure out how to do it in very simple ones
But if
first.
the model doesn't describe what people are doing in the game, I don't.
Well, that's another thing about psychometrics. You
That
don't
was
have
my
to believe
question.
the models.
Actually, that was my question.
Like
So
you-
here's the psychologist who wants to chime in. I have the feeling there's more in this talk that I would like to hear. So can we let her give the rest of the talk and then discuss? This is what psychologists do. They do something that's very hard called respect of the speaker. So let's
But the questions are a sign of respect.
Oh, right, you need to point something out. Noah's frozen over. The economists are complaining that she's using the neoclassical model of choice.
Wow. So I just skipped like half of my talk, and wanted to get to perhaps something that you might see value in. So here is simulation results from this Peg Solitaire game, in which I had simulated populations. I will just show you that real quick, which had either high or low capability and high or low motivation. And then I simulated records from these 4 different populations, game records. And I looked at their total score on the game, so just how they did. And then I also looked at their moves and estimated the MDP parameters. And if you just look at mean total score, your high ability, high motivation students, you can tell who they are every time. That is not a problem. And that's what a lot of tests just do. That's all we're concerned about, saying who's the best, who's going to get the credential. But if you're interested in actually knowing the difference between your high ability, low motivation students and low ability, high motivation students, you cannot tell that based on the outcome score. But when I estimated the parameters, I could distinguish all 4 groups very cleanly. This is what you get out of the model. The actions give you distinctions, subtle distinctions in the way they behave based on what their goals, their motivation, and their abilities are. Now, the PBS Microbes game, which if you read the paper, you saw this. This is a game with actual students on the PBS Kids website. You play the part of a microbe. You have to survive in a tank of water based on how you've configured your microbe. So here I'll skip over exactly how I set up the model. We can estimate capability. So this is one study I did where I just focused on capability, and I found that the estimation of capability correlated with post-test results much better than IRT models that were based on, again, the outcome scores, even if they use the multiple trial partial credit model for the outcome scores. So we are getting more information out of the action students take. And this one does have a stochastic part to it. So one of the issues is students can be taking the correct actions, but get a poor result, not because they don't understand the cell biology, but because they're really bad at driving the microbe around. So this is, a cost of some of these educational games is they introduce this extra construct irrelevant variance, which we can get around by looking at the actions they take rather than the results.
So how do you fix the transitions? Is that obvious how you?
So in this case, this was an interesting one because they were stochastic transitions. What I did is I actually used the game records themselves to estimate what was the most probable success states, and I use those as I use the probabilities themselves out of the data.
Oh, I see. So you fit that on the population averages, and then take that to the analysis of the data, on the actual choices of individuals.
Right. That wasn't within the model. That was an exterior analysis.
So there's a lot of other choices you might have made.
So another way to deal with the transition parameters is to assume that they actually encode the student's understanding of what the ideal microbe configuration is to win the game. And so if we assume that students have this ideal configuration in their mind, we can estimate what the students believe. This is where the belief is equated with their knowledge or understanding of the cell biology, because they should know for this particular level that I'm showing here, there was sunlight and there was no food. They should know that they need both chloroplasts and mitochondria. But if they don't understand how these organelles work, they may think they only need chloroplasts or only mitochondria. And you do see that those who understand they need both correlated much higher, had much higher estimates on their post-test results than those who were confused. So these are the sort of thing that we can get out. I don't know if I have any time left.
Well, you do. We don't.
I just want to at least talk a little bit about this since Bob had introduced the SimCity EDU challenge. I won't go through all of it. The important thing here, and I modeled a slightly different version of the game than Bob did, and it's power and pollution that they had to optimize simultaneously. There was no way I could, even with the cut down game, there's no way I could simulate all of the actions or all of the states. So I focused in on the actions that involved the power plants because they were really key to solving the scenario. and focused on the game states related to those. Even with this cutting it down, the total number of states was almost 3 million. Luckily, given the starting configuration, only 25,000 of those were reachable. The computational complexity of a game like this, running it through an MDP model, does become prohibitive very quickly.
Have you thought about using some approximate dynamic programming? You have all these methods which are used to sort of approximate the optimality, which are much cheaper.
Well, the difficulty is because I'm not just looking for the optimal policy, I actually have to have an estimation for every possible action in every possible state.
Which is sort of approximating that.
I'd be interested in talking to you about how to do that, because I don't, my code doesn't do that. So the rewards, which was touched on a couple times, if you get the air quality index below 100 and don't suffer a blackout, you can get a bronze medal. You can get a silver medal either by having the power never even be low or getting the air quality index below 50. If you get all three of these, you get a gold medal.
So you're getting rewarded. You know what the quality is and what's happening as you go.
Yes, you know what the air quality index is.
I think that's intrinsically rewarding. If I'm taking actions that are reducing pollution or driving people out of the city, I'm winning the game.
These are actually your measures
here. In that sense,
here.
I am getting rewarded by that. Okay.
There is, yes. So for this game, what I focused in on was different hypotheses about the goal structure, assuming that students who were trying to optimize both pollution and power would be in line with what we set up for them in terms of the rewards, in that each medal, each additional objective would be increased. There might be a set of students who want to win, but that's all they care about. They're not, they're sort of a lower motivation class. But then our real interest was in these possible populations, people who are only trying to optimize the pollution or the power. Sorry about the background. I don't know how that happened. So basically, we were able to classify the students based on which reward structure fit their data set best, their data. And we did see quite a big variety of student behaviors based on this. However, there were 53 students who fit none of these. So that's one really important takeaway, and I think it's been mentioned before, which is that if these cognitive models don't fit, we simplified down to a certain number of actions and certain number of state variables that we're following. In the case that we are not modeling the actions that the students think are important, or not modeling the state variables they're trying to optimize, like sim happiness, they're going to be a poor fit for the model. And you see those here. Here's our beta estimates for students based on the reward structure of their choice, but for our non-fitting students, the model just didn't work. I think I will end it there.
Just a quick question about the number of different ways that you can approximate the solution to a dynamic program, or what could be going on when people are making mistakes. I think your version of it is a little bit like, it's as if somebody had worked out the entire solution to the program correctly, and then felt that their hand trembled. And they took account. I mean, they're being a very sophisticated donor.
So, I mean, I guess I disagree with that, because I think the students know what they're trying to work toward. They may not know how to get there. And for each state that they find themselves in, they have choices of what actions to take. So they may not see exactly what the results of their fifth ahead action is going to be, but they know that they want this action to get them closer to the goal in some way.
Yeah, I'm not sure we disagree on that. I think that's what it's a question of where you throw the randomness in. And you could throw it in terms of a confusion about the structure of the game,
right,
or a complete understanding of the structure of the game and a worry that your hand trembles. And I think technically what you're doing is giving them a complete understanding of a tremble, as opposed to saying they're genuinely doping. And I'm not, I mean, they're different versions of stochastic choice.
Right.
And they're very hard to distinguish.
No, I hear what you're saying. And that's an interesting point.
They're just very, there's no, I don't think there's any theory right now that works it out very well. So you're doing, I think it's very, very badly done. So
I think one thing that's interesting, you know, I'm not sure if this was your point, but you mentioned, you know, kind of seeing out the whole game and knowing what all the moves should be. One really interesting parameter that I have not played with yet is the discount parameter. So, you know, generally a discount parameter is assumed to reflect real change in value, that the value is different, right, to me now than it would be in the future. But it can also, in this context, be seen to reflect how well can the student evaluate the value of their move 5 moves from now. And we might want to estimate that as well as a sort of visibility parameter for the problem solver.
What's interesting about the games you're looking at is that the pen game, you can look at the board without touching anything, and you can say, okay, 1, 2, 3, again, 7 moves, and I'm out, and figure out the exact right way to do it, and then make your moves, right?
Yes.
With this, you can't do that.
No.
Right? You really, for example, you don't know what the marginal impact of bulldozing is until you bulldoze, right? Then something happens. Oops, you know, I better change direction. So I mean, what's interesting about the 2 things you're doing is that one of them, people really should be able to plan completely what the right move is and do it. And you could say something about their cognitive ability by saying that, yeah, they could indeed plan 7 moves, it's 8 pieces, 7 moves ahead. Then that says something. But the other one, they really need to do a trial and error. It's a very different. I think it's kind of importantly different.
Right.
Those 2 different games. I also get the impression, again, my recollection of computer games of this sort is they oftentimes will have adaptive elements to them. So like, almost like Pong. If you ever played Pong before, dating myself, I guess, but there's only one thing that's hard about Pong, right? And that is that if someone hits the ball to you and you miss it, the next ball comes out and it's real slow. And once you hit it, it goes back. And as you start getting more hits, it starts speeding up, right? And one of the things that games like this often do is if you start making a couple of good moves, it starts throwing some things at you to make your moves harder, right? And I'm not sure if SimCity does that, but
Yeah,
that's also something that I think is kind of interesting. Earlier we were talking about decision under stress, and one thing that's really neat about a model like this is you can, in effect, based on someone doing smart things, start making it harder on them, adding some stress or timing elements to it to kind of get a sense of how they'll react into those circumstances.
Yes.
So the game's going to have an interesting model, I guess, to look at some of these.
And one thing I do want to point out is this particular model is, I think, appropriate for strategic decision-making games and simulations. It's not appropriate for all games. I mean, just because you brought up Pong, you know, I wouldn't throw an MDP at a Pong game, right? You'd want a different model. But I think in a case that part of the point of the game is to make decisions that are going to have strategic impact going forward. This model is not perfect, but it gets us a lot more than just looking at the outcome scores from these tasks.
So now I wanted to comment on this belief on T. There is a large literature in neuroscience that tries to address the way in which people face uncertainty about the work that they are working in. And there are broadly 2 classes of model. One is enforcement and the other one is model-based. And I think you are assuming the model-based without the justification for this, because it is known that there is heterogeneity in the way in which people address this uncertainty. Maybe they don't even try to build the model, so they don't have a set of T's and probability distribution on them and updating them. They are doing something much simpler, trying to find an association between an action and an outcome. So,
those people, there would only be the immediate reward. And so,
no.
Wouldn't there? That's what you're saying. There would only be the immediate reward.
No, they don't try to build a complex model of the way in which the state, the current state and the current action.
So they're making a decision based on What?
on an estimated Q without a structure of T.
And their estimated Q then would be something like they're building it into their, I would claim they're building it into their reward structure. So a reinforcement learning model is based on the same principles, except.
But it doesn't have to be an explicit reward structure. Kind of like the paper that we
No,
talked
not
about.
explicit at all. This
No.
is internal.
No, I know, but I'm saying explicit in the sense of writing down this particular Markov decision. You can approximate from the choices and say it's either like a reinforcement learning model or from, it seems to me it makes need some finer distinctions to separate those, right?
And since you are there, why not use direct analysis like magnetic resonance to identify it? I'm serious.
So you'd look at neural substrates.
Yes.
How they would activate. in place.
Yes.
Okay.
You laugh at this.
No, I love it. I want you to bring your equipment over and let's run some students through SimCity. But yeah, there are lots of other ways you can approach this. I agree.
I think we have time for one more question. For you.
You're the discussor, aren't you?
I was asked to be one, but
Yes. Sorry, you didn't
do
know?
so with
No.
some serious trepidation.
No, go ahead.
Correctly
Well,
so.
since I knew that this was at the end of the day of a conference that Jim organized, I only had 2 slots because I knew.
Yeah.